start up again right now. This is going to be the group that doesn't get into the read my mind exercise. All right, so here's the scenario. I have two objects heading towards each other. They're going to collide. They collide, and then they separate. So, let's draw up just an absolutely incredible sketch here. Objects A and B are heading towards each other. They are going to collide at some point. And then they will separate at some point. In this particular scenario, I have them going in opposite directions. They don't necessarily have to. As with anything's collide, they sometimes they bounce off each other. Sometimes one is so overwhelms the other one that it just sort of follows. While contact is taking place, there are three things that are common to both object A and object B. There are three things that are the same for A as they are for B. What are the three things? Now, before anyone yells out anything, let's add a level of excitement to it.
Force exerted.
I will allow you to expand on that just a little bit more.
Okay, the force exerted by A to B is the same force exerted from B to A when they collide.
So close. Let's narrow that down before we just left two words out, maybe four.
I think this is like almost like the problem we had just now in the master set about the truck hitting the car and how they both have the same like impact even though one is bigger than the other.
It is very much like that.
Are we saying that they both have the same amount of impulse when they hit each other?
I want to stay away from the word impulse at the moment.
Okay.
Same magnitude?
There we go. That's the key right there. I think that's what you were thinking, but why is it, when Brittany said they have the same force, why is that technically not right?
Because there could be multiple forces.
There's mass and
Not multiple forces.
acceleration are different.
No,
Maybe.
not that.
Okay.
When A hits B, what direction is that force acting on B?
To the right.
Which way is the force that B exerts, which way does B exert a force on A?
To the left.
Force is a vector, so the directions are opposite. But it is the same magnitude of force. All right, so I'm going to put that over here. Same magnitude. I'm going to do a shorthand notation for this. So verbally, same magnitude of force. Shorthand notation, the force on A from B is equal to the negative of the force on B from A. The minus sign just means opposite directions. The flipping of the subscripts just is the force on A and the force on B. This is the force on A, this is the force on B. So shorthand notation for, well, actually Newton's third law of motion for those who are purists. All right. Two more to go. That's one of the three things that are common to both. The magnitude of force.
Are these on a ground?
No.
There's no friction, is there?
No. And I will say that we can, this right here accounts for any force acting between the two. So the way, the scenario I've set up, it's a normal force, but you don't have to list any other forces. We've got forces taken care of. All right, what else is the same for both?
Mass.
Not necessarily.
Sorry, guys.
The acceleration after they collide.
It depends on what their mass is. The magnitude of the force is the same, but if their masses are different, their accelerations would definitely have different magnitudes.
Gotcha. Is it the force of gravity?
We've already taken care of all the forces.
Okay.
Force of gravity, I'm not gonna put it up there, but if anyone else mentions a force, I will start adding the body parts. Forces are already taken care
I
of.
thought you said gravity wasn't considered a force.
Oh, it is a force. Force of gravity, weight, those are both forces.
It's indistinguishable from a force.
Got it, okay.
Are you getting into the curvature of space?
Yes.
You are. Are you?
I just see the force and gravity being the same, but so that's why I said that.
Yeah, well. Not where I wanted to go. All right. Force of gravity between the A and what?
The ground.
Okay, that would depend if their masses are the same or not, which mass is already created the head. There is a force of gravity between objects A and object B that are acting on each other, which would be equal in magnitude, but that's, again, covered in this right here.
Velocity.
No, that, there's no reason for the velocity to be the same while they're touching each other. Well, actually, they start out moving in opposite directions, so.
Would like a point of origin or a starting point be the same, like whenever they initially collide with each other? I don't know if that's what you're looking for.
It depends.
Okay.
Why don't we just say that's probably not the right track to go down,
Okay.
but maybe, depends on how you want to define those things. Luis,
Do they have the same displacement? Like,
keep going.
I don't know, like, is it, since they're all both going the same direction, I'm assuming they'll have the same displacement, 'cause, I don't know. I'm just assuming.
And remember, the question is while they're touching each other. Do they have the same displacement while they're touching each other?
Yes.
Well, it depends on where they started. They started.
Not, if you, while they're touching each other, so when they make contact, that's their starting point. And then, so they hit like this, and then they shift. When they separate, they don't separate at the same place where they make contact.
Okay.
So displacement, I don't know if that was your intent, but go for it. Luis, as Luis said, so the displacement of A is equal to the displacement of B. And one more, and I will say the last one is usually the one that people don't remember, or the people, it's usually the third one people come up with, and it's probably because it is so incredibly obvious, people don't even think about it. And I'm just gonna go ahead and tell you I believe it is the most obscure clue I ever give in this course. It is the name of a Bobby Sherman song.
Bobby Sherman.
You might wanna ask it, and that's why it's my most obscure clue. And as a side note, a couple years ago, I had an older student who actually had been to a Bobby Sherman concert. His sister was a huge fan.
So it's while they're touching each other.
Yes. Might also be the name of a Pink Floyd song.
Is it the time of their impact?
What do you mean by time of impact?
Like the time that they start touching each other? Or the collision, or?
The point of collision.
So they're not necessarily, but you're almost there. You got half of it.
Okay.
The place that they touch.
Touching a period. Touching period.
Say it again.
Touching.
What-
The
what
no
about-
contact.
Sorry, I missed. So are you connecting up with time?
I was just, what's the same about them? They're touching.
They are touching, yes, that is true. I think that's sort of throwing into that.
Okay.
Hannah, was that?
Yeah, where they are in contact, the point of contact.
I think that's sort of bundled up into displacement here. And this goes back to something said earlier, they're not necessarily hitting each other for this. I keep thinking of nuances. And this is not necessarily the time to do with the nuances. But what the heck, let's do them. There was a question earlier about whether the origins, or mentioned earlier, the origins being the same or the starting point being the same. The origins are not necessarily the same. You could have two different systems there where B has some starting point here, A has some starting point over there, or you count this as the starting point of contact since that's the problem. But these things have some depth to them. So if you wanted, where's the location of B, usually you use the center of mass, so the location of B at point of contact is there, the location of A at point of contact is there. When they separate though, the centers move the same amount. And so that, in the same direction, and so that's why I'm going with the displacement being the same. A lot of words, and I hope I didn't leave one out. All right, so. Okay, that's just, okay.
Is it the time in between like, is it, I guess, negative acceleration and then when it's at rest?
So, time of acceleration from when to when?
Like when it starts to decelerate,
So when they first make contact?
yeah, and then when it stops? Are those the same, or is that?
When do they stop?
I don't think they stop. I think they just change direction.
Okay. Do they change direction at the same time?
Before it goes into positive acceleration?
So, I think at this point I'm gonna put people out of their misery. You were so close. You were almost there. From point of contact to point of separation, that time is the same. They touch each other for the exact same amount of time. It's not necessarily from point of contact to when they stop, or to when one of them stops. It's from beginning to end of contact. They touch each other for the same amount of time. And that's one that people, I think, is ultimately an obvious thing. You're touching your chairs right now, the chair is touching you. When you stand up, both of them stop at the same time. So it's not necessarily a specific time, because you could have the person watching B could start the stopwatch at any point. The person watching A could start at any point. So the time they actually touch, they don't necessarily hit at the same time from their points of view, but they do touch each other for the same amount of time. And this is one of those things that I said earlier, quantum physics, when you think you know everything and suddenly we just want to make you question everything. I've tried to think, is there in quantum physics a way for them not to touch each other for the same amount of time? And I don't. It's questionable whether that's even possible in quantum physics.
I mean, the word touch starts to lose its meaning in quantum physics.
Yeah, we would expand it to interact. Can they interact with each other for a different amount of time? All right, so why do we go through this exercise besides just the joy of having you
I mean,
go through that?
if one of them experiences a different amount of time itself, maybe.
And I've also, I want to just make this a quick side note. If the interaction involves exchanging particles, that they're shooting one particle at another. For instance, if I take this marker and I let go and it falls. Bad example, because I know what your response is going to be. If you take two magnets and you put them near each other, they attract or repel, or somehow there's an interaction there. How does one magnet know the other magnet exists? So in physics, they dealt with this and trying to think of, all right, so we've got to come up with an answer. Got to act like we know what's going on. And they came up with this idea that it's exchanging particles back and forth. So if they're exchanging particles back and forth, there is a scenario in which one object could sort of be moving away from the other object. And so this one would get hit before this one does. Anyway,
touching without really touching.
yeah,
That's where y'all come up with the interaction.
yeah, and, yeah, I've spent more on this than I wanted to, so apologies. But for those who want to relive it, it's being recorded. And the person didn't die. But he's seriously maimed. All right.
So,
I have a cousin Andy who was born without this part of his arm. Nah, I'll save the Andy story for later. All right, so what is this? Why did I have you go through this? If you combine these two concepts right here, this is chapter 7, and you get into the idea of work and energy. If you combine the first and the third one together, you get into chapter 6, with the idea of impulse and momentum. So you there. The foundation of all of this is still Newton's third law, or Newton's laws. But we're now going to sort of bury that. And the reason why is if I have an impact, if I have two objects that are going to interact with each other and then either stick together or bounce off or whatever they end up doing. If I was applying Newton's laws to it, I would need to know how the force changes as these two objects interact with each other. That is not easy to do. But if we look at impulse and momentum, I don't care what happens while they're interacting. I can predict what's going to happen if I know what's going on beforehand with what's going on afterwards. What's happening in the middle, don't care about, just care about what before and after. I'm now going to take you into a mathematical derivation. And I know most of you are thinking, all right, finally, some hardcore math here. For the rest of you, for those couple of people who are not just ultimately excited by math derivations, I am doing this just so that you can see that we're starting with these basic principles, this idea that they exert the same magnitude of force on each other, but opposite directions, and they touch each other for the same amount of time. I'm going to start with that. I'm going to go through the derivation, come out with a conclusion in the end. If the math is beyond you, just let it flow over you. Still sort of pay attention, but let it flow, sweep over you. Just imagine you are being, ignorance is just being washed away, and that at some point in your life, it will make sense. I'm not going to ask you to regurgitate this, but I want you to see that there is some connection as opposed to going, well, that's true, and then boom, obviously this is true. I want you to see that there is some flow to it all. And it's a math derivation, so the rest of you are just excited. So we're going to start out with the force on A from B is equal to the negative of the force on B from A. Newton's third law. I'm going to multiply times the time that they're touching each other. So this is the force on A from B times the time of A is equal to the force on B from A negative times the time that B is touching A. Since the times are the same, just multiply. Math people tell me as long as I multiply both sides by the same thing, I'm good. If the math people are lying to us, then pretty much all of physics is gone. All right, Newton's second law. What is Newton's second law of motion? The chapter 4 stuff. The most important equation, in my opinion, in all of physics.
force equals mass times acceleration.
So this force right here would be the mass of A times the acceleration of A times the amount of time that A is touching is equal to the negative mass of B times the acceleration of B times the time they're touching. So all I did was I take that force and I just set it equal to mass times acceleration. Now I have this acceleration times time. Let's come back over here. What is acceleration?
Change Velocity.
Yeah. If I multiply both sides by that time, I get acceleration times time is equal to the change in velocity. So all I'm gonna do is over there is where I have acceleration times time, is I'm gonna put in change in velocity. So this is the mass of A times the change in velocity of A is equal to the negative mass of B times the change in velocity of B. Change. What am I subtracting from what?
The final versus the start.
Say it again?
The final minus the start.
Yes. So this is mass of A times V final of A minus V initial of A is equal to negative mass of B times V final of B minus V final, initial of B. The next line is a real nuisance just because there's a bunch of subscripts, just warning you, then we're gonna simplify it. And don't worry, we're heading to something that will just absolutely make your life worth living. I'm gonna distribute. So multiply times the first thing, then times the second thing. And over here, distributing negative mass of B, so negative mass of B, V final B, minus, not much longer. The negatives cancel out, make it positive, so mass of B, the initial of B. All right. Obviously, I got mass times velocity 4 times. Physicists don't like writing, so they come up with a shorthand if they can. So what I'm gonna do is I'm just gonna use this letter P to represent mass times velocity, just so I don't have to keep writing it again and again. So I got P final of A minus P initial of A is equal negative P final of B plus P initial of B. So just using P instead of NV because I don't feel like writing NV.